My name is Austin Nash, and today I'm going to present my talk titled Robust Control Co-Design with Receding-Horizon MPC. And this is on behalf of my co-authors, Dr. Pangborn and Dr. Jain. I want to start today's talk with some high-level motivation and background for our work before I get into talking about our algorithm itself and some of the results that we've seen. So Control Co-Design, or CCD, is starting to gain renewed attention as performance requirements become more strict and more stringent across a range of sectors. And our specific motivating example for this is in electrified aircraft, where new generations of these systems now need to dissipate really high levels of waste heat in short transient bursts. And so Control Co-Design really offers a nice, promising solution for coordinating the physical design of a vehicle system with its governing closed-loop control algorithm. So CCD has largely been limited more so to the design of static optimal control policies in the literature, ranging from things like LQR to H infinity. And in fact, the design community typically emphasizes the use of open loop control policies as opposed to closed loop control policies. And so what we really want to do is start leveraging more dynamic control policies such as model predictive control in CCD frameworks to take advantage of the ability to handle things like state and input constraints, but also to take advantage of the ability to have preview control for things like pre-cooling in an aircraft context. So there has been a little bit of recent work on integrating MPC into CCD, but this work has really only started to scratch the surface. And I've cited a few here, but none of these works consider robust MPC within CCD. And so that's where our algorithm comes in. I'm going to present an algorithm where we optimize a recursive, robust model predictive control, or RMPC control policy within a CCD algorithm. And our policy allows us to develop offline a controller with a closed form solution that we can then implement online and be able to satisfy robust constraints. And now I want to get into talking about the algorithm itself. And I'll start with a little overview of the algorithm. It is nested co-design. And so all of our control design, our MPC design, comes within an inner loop that's nested within an outer plant loop. And so in that outer plant loop, we're just looking to minimize some user-defined cost function. And then what we do is we assume some nominal set of disturbances, D, for each kth time step. We have NT time steps. And then we also assume there's some bounded uncertainty on the disturbance variables at each time step. But we assume that we know the uncertainty does lie within some known set, big W. And what we're going to do with our inner recursive MPC loop is attempt to handle things like control constraints, account for that bounded uncertainty, and we're going to look to design a combination of feed-forward control variables and feedback control gains that are going to help us meet transient state constraints online in response to that disturbance uncertainty. So in block diagram form, we're going to take those control variables, those feed-forward variables, and the feedback gains, implement them online, and be able to adjust and reject the uncertainty in those disturbances to meet our state constraints. And so the outer plant loop is pretty simple. We just look to minimize some user-defined cost function J, and our main decision variables are some plant design parameters P, and some nominal or initial system state and set of control variables X naught and U naught. Within that plant loop, our main constraints are the set of binary variables H sub k at each kth time step. And that's a feasibility constraint that is passed back out to that outer loop from our MPC loop in the middle, that inner loop, I should say. And so we're requiring a feasible RMPC solution at each time step. And then we also impose nonlinear state constraints, constraining our states to be on our nonlinear model to be within some bounded set X at each time step. And that control input UK at each time step that we use to simulate on the nonlinear model actually comes from the solution to the nested RMPC problem at each time step. So the MPC loop gives us feasibility information and the control input that we then use in the outer loop. And so that inner RMPC loop, we are leveraging a min-max robust MPC policy. So we're saying for the worst case disturbances, we'd like to minimize some control cost function, leveraging our inner loop decision variables, which are mainly these feed-forward control variables at each time step. And then the feedback gains at each step in our horizon are passed into that RMPC problem from the outer loop, and they're then leveraged in computing the solution to the RMPC policy. And so for constraints in that MPC loop, it's typical sets of linear MPC constraints, so linear state constraints for each time horizon, constraints on our inputs, and then we also enforce that bounded disturbance uncertainty constraint. And so that our MPC problem then gives us feasibility information and our total control input at each time step to pass back to the outer loop. And I should note that future work is going to look at studying theoretical guarantees for recursive feasibility of our MPC policies where we have to successively linearize the system due to things like highly nonlinear operating points. But the way that our algorithm flows here briefly is we can go ahead and initialize all of our variables and compute the outer loop objective function, and then we start looping through each kth time step in our time horizon. And so at each time step, we can linearize and discretize that system and compute our feedback gains that go into the MPC problem. We then solve the MPC problem and keep storing our control variables and gains at each time step and give those gains and variables and the feasibility info back to the outer loop. And we just continue stepping through each time step until we're able to evaluate the total outer loop feasibility for that iteration. And then we can update decision variables accordingly and just repeat until convergence. And so really what we get out of the RCCD algorithm is the following. Not only do we get our optimal decision variables, P star, X naught star, and U naught star, but we also get sample scheduled sets of those feed-forward control variables and feedback control gains that we were solving for at each time step in that nested inner RMPC loop. And so what we're saying is we store those feed-forward variables and those feedback gains that we compute offline, and then when we take that resulting plant and controller online, we can apply those variables and gains without any online optimization so that we can meet our transient state constraints, even though we didn't know the exact disturbances a priori. And so to illustrate the efficacy of this approach, I'm going to go through a short case study. But first, I want to present the system that we're leveraging in our case study. It's a dual tank thermal management system that's indicative of something you would find in advanced aircraft, where fuel can be used not only to feed the engine, but also to store and dissipate thermal energy. And so we've got these two tanks with fuel in them, or working fluid, if you will, and we assume we have control authority over the mass flow rates leaving each of these tanks. And those flow rates mix, and essentially what we're trying to do is we'd like to keep this heater temperature here, this fluid temperature in the heater, to within some bounded region in the presence of these uncertain disturbances, these heat pulses that we're pulsing in due to something like electronics cooling, and then the fuel that must exit the loop to feed the engine. So at a high level, we're looking to, our cost function is going to be, we want to minimize the initial amount of working fluid in the system. And then in terms of transients, we'd like to use our control authority to maintain a heater temperature in a certain region in the presence of these two disturbances here. And we also have plant parameters that we're designing in the co-design algorithm. And the two that I'll mention here are CH and CC, the heater and cooler fluid capacitances, which essentially correlate to the size of those components. And so to evaluate our algorithm, we're going to benchmark against this baseline, our open loop CCD algorithm. And this is something that you might find in the design literature, a more conventional CCD algorithm, where we assume that the future is known perfectly in terms of disturbances, and we use a single horizon to just optimize an entire set of feed-forward control variables at once. So that's, again, typical of something you might find in the design literature. And what happens when we go ahead and run both our proposed algorithm and the baseline algorithm is we see some pretty interesting things happen. First, the optimal fluid mass for our algorithm was 2.84 kilograms, which is only 1% higher than the 2.81 kilograms given by the baseline algorithm. The difference is that with our algorithm, we're allowed to, we're able to also account for robustness to disturbance uncertainty for all those disturbance, that additive disturbance uncertainty that we accounted for in our CCD algorithm. And to illustrate that graphically, I'm going to present a short set of case study results here. So in the top left, we have our sets of disturbance profiles. And so we've got Q.H, the heat pulses on the left, and M.E, the flow rates on the right. And the dashed lines for each case represent, for each disturbance, represent the CCD, or the disturbance profile that we planned for in our algorithm. And then the solid lines represent an underplanned case where we're saying, what happens if we underplanned in the algorithm offline and the disturbances we actually see online are actually higher in magnitude? Conversely, the dotted lines here show or illustrate what happens if we overplanned in our algorithm and the disturbances we see online are actually smaller than what we had planned for. And then down here on the bottom left, we see the heater temperature signals for both our proposed algorithm in blue and in black and gray, the baseline algorithm for both the overplanned and underplanned case. And what we see is that with our algorithm, we're able to use our control authority to make sure that heater temperature stays within the allowable region that's banded in red there the entire time, even though we didn't know those disturbances beforehand. Conversely, the baseline algorithm is not able to meet those state constraints when we didn't know the disturbances a priori. And over here on the right is just the control signals, the control authority used in regulating that heater outlet temperature for each case. And so really the takeaway here is that with our RCCD policy, we optimize everything offline, and we've got a closed form solution that we're then able to implement online to make sure we meet state constraints, even though we didn't know those disturbances beforehand. And so just to summarize here, our goal of this work was really to start incorporating robust MPC into a control co-design framework. And we did so by leveraging what we're calling an RCCD policy, where we leverage a combination of feed-forward control and feedback control online to meet our constraints in the presence of uncertainty. And our case study showed that we were able to do so for a notional dual tank thermal management system quite well. And so I'll finish by thanking everyone for logging on. And I also want to thank the Office of Naval Research for supporting some of this research, and also my co-authors, Pangborn and Jain. So I'll stop and take any questions at this time. Thank you.